and another talk about axiom proposal. But okay, let's start with Igor. Thank you.
Okay, so yeah, let's pick up from where we left it yesterday. So basically, what I told you yesterday is the main.
Yeah, I'll remove it. Sorry.
The main technique to search for dark matter actions, that is this CTV haloscope, and all the R&D that is being done to improve this concept and to make it valid at higher masses. So there's a strong motivation. So we have ADMX basically with a sensitivity sufficient to detect most QCD action models as dark matter candidates in a mass range in the order of the micro electron volt, and they are running right now. So if there is an action there, it will be detected soon. But what is not so clear, and this is the motivation for this R&D, is to apply this technique to actions with higher masses. And we have all these projects that I mentioned that are much more recent than ADMX, like KSTAT, Quack, Stravers, and so on, CAP Institute for these activities. Okay, so so far this is all what I wanted to say about the action haloscope. If you have questions remaining from yesterday, it's now the moment to make them. And the next slides are about more radical departure from the original haloscope concept to look for dark matter actions in other mass ranges, in particular to substantially higher mass values in which it's not clear that the haloscope can be applied, the conventional haloscope can be applied. Yeah.
Sorry, I'm on the mic situation. Thank you. Why did ADMX and these other experiments pick the mass range that they did?
Why they decided to do that? So for the case of ADMX, it was a bit okay. They are in a part of the mass range that is very well motivated for action. But okay, they started many years ago. I already mentioned yesterday when ADMX started, the lambda CDM model was not yet established as it is now. So I remember the very early papers from ADMX, they were still pointing to an action mass would correspond to 100% of the critical cosmological density. Where that energy didn't exist as a concept yet. Well, it was not to the start. So this points to lower masses than the ones that are now preferred in the simplistic models in which you only consider realignment action. Now we have a better view of what is happening. We have all these model freedom better understood, and okay, in reality, they develop select a very specific mass range as the best motivated. It's much wider this room. So it turns out that also the reason is more practical because it's easier to look for dark matter actions at lower masses because you have a bigger cavity. So so somehow all this is why ADMX focused to actions in the micro. But then it turns out that they are a little bit on the left of the best motivated range, so there is a strong motivation to go to higher masses. So a very original idea that is the magnetized vision theorem. Just what I want to mention. There are many papers in the last, let's say, 5 to 10 years proposing new ways to detect actions, and I will not review all of them. Many of them they are just papers they never go to the lab. So I pick up a selection of ideas that I think they are a bit more solid because they are experimental groups really doing something. In some cases, important projects that we'll see the light soon. So the first one is this magnetized dish antenna, which is a very simple concept that it can be seen like a haloscope idea, but without any resonance. So you have only a piece of a mirror, a surface. It's enough with a surface that change an interface between two media with different dielectric constants. And then if this surface is magnetized, so there's a magnetic field close to the surface, then in the background action field from dark matter should induce an emission of electromagnetic waves or photons perpendicular to the surface. So this emission, of course, is extremely tiny, and how to detect it. So the idea is to use a spherical dish so that all these emissions from all the dish are concentrated in a single point, and you can increase a little bit the signal to ratio. Of course, you don't have any resonance, so the emission that you expect from this process doesn't have this Q factor that we have in haloscopes. But one could, in principle, compensate this absence of this amplification by using an extremely large area. Somehow you have here the correspondence between area of emission and Q factor that they use. So how do you go from the power getting from a single dish with a resonance to a haloscope with a resonance? Even with this trick, you need to go to areas which are probably non-realistic, something of the order of 100 square meters. These antennas exist, but the problem is the magnetic. Nevertheless, there's going to be an implementation of this idea in Hamburg. It's called the BRASS project, which basically they have turned a little bit the original idea, and what they have is it's a flat surface magnetized with permanent magnets. So the emission is parallel, and then is reflected by a dish to a receiver. The nice thing of this idea is that because you don't have a resonance, you could in principle be sensitive to any action mass at the same time. So basically the bandwidth of the experiment is fixed by your receiver, not so much by the experiment. So this is very nice because this is the only idea in the market that allows for a broadband search. Well, when you put the numbers, you will see later in the plot that the prospects for this experiment are barely sufficient to reach the QC reaction. So it's going to be challenging. So this idea was later on refined and evolved to what is now known as dielectric haloscopes, which is a hybrid between this magnetized dish idea and the conventional haloscope. So somewhere in between. So we recover some resonance, some amplification resonance. So the idea is to stack many of these interfaces. In this case, we need them to be transparent, so they are not mirror. The first one is a mirror, but the next one is a set of dielectric discs. So and all this is embedded in a magnetic field. So from each of these surfaces, you expect this emission of photons due to the dark matter field, and then you can compare with the single mirror idea. Then you add up every dielectric that you put. In principle, you add up power, so you get an enhancement. Not only simply because you add these mirrors, but because you get some mild resonances in between the mirrors, and you have some constructive interference between the different waves coming from the different mirrors. So you have to place them very carefully to gain something at the end. So at the end, you get a final emission that you can concentrate and detect, which is the original emission boosted by a factor that is the number of dishes plus something else.
Just basic question about the setup. Is the expectation that the photons won't be able to go through the dielectric discs?
they go through these electric discs are like semi-transparent, so a fraction goes through and a fraction goes back and resonates. So it's at the end you have to take into account all these together. So you have some of the waves resonating, going back and resonating, a fraction going through. And if you do this carefully, all this has to be simulated carefully and placing the disc in the right places. At the end, you get an enhancement of the signal in some frequency range, of course. So we are going back to the haloscope idea, but in a milder way. So this window is much larger than the typical haloscope.
Okay, so you're going to get more photons than you expect because of the oscillation of the axioms? Or fewer? It would a positive signal be more photons?
You enhance your signal with this resonance, and both the resonance and the constructive interference between the emissions of the different.
Okay, thank you.
They call it this boost factor in this type of experiment because it's not really only the Q factor like the haloscope. It's something more.
And is there any background for something like this?
Background? Yes, the same as in haloscopes. These are microwave photosensors, so you will have thermal emission. The technology will give you also some temperature photosensors. So, yeah. So this concept has been pursued experimentally quite strongly by a relatively recent collaboration called MAX. And this is the final goal of the experiment. So this is an implementation of this concept. You can see here that there are many disks stacked one after another. I think the final goal is to use 80 disks. And all this is embedded in a very strong 10 Tesla dipole magnet, which is by itself also a challenging magnet that should be built specifically for this experiment. And then, okay, this is reflected and received here. And in principle, on the paper, this concept could have very competitive sensitivity for masses. You can see here quite but more to the right than 80 So we are talking about masses of the order of 100 micro electron volts, I mean 200, between 80 to 200 micro electron volts. Is one of the leading projects at the moment in this area. But of course, there is a lot of R&D still to be done to reach this point. So there is a prototype that is going to be installed in an existing magnet at CERN with less amount of risk. The challenge here for this magnet is not trivial to so I didn't mention the dimension, but this is of the order of the meter scale, so both diameter and the length meter. So it's a big magnet. Also, there is some stranding here to do. This is not completely broadband. You are sensitive for a given configuration of the disk. You are sensitive to a relatively narrow, not as narrow as the haloscope, but relatively narrow band, and you want to move this band. And move this band means to rearrange all these disks. So this means to move 80 disks in a cryogenic environment with a lot of precision. So this is a challenge, which is being addressed by this group. So yeah, Max, you can remember his name because he's one of the major players in Europe now. Well, I go a little bit aside of this presentation of experiments by mentioning directional effects. Because you probably have heard in other talks about the possibility it has been studied a lot in the wind community. So the possibility to measure the direction of the dark matter, not just a signal, but to measure where is the incoming direction. It would give a fantastic signature of the origin of the dark matter. It would confirm that what we are seeing is the dark matter, because we expect that this dark matter from the standpoint of the Earth, should have a clear velocity distribution due to the movement of the Earth in the dark matter halo. So it turns out that there is an equivalent in actions, and it's extremely easy. If one day we see an action signal, it would be much easier than in case of winds to make a experiment that is sensitive to the direction. And this is because we are dealing with a wave. So a very simple way to see this: if you have an experiment which is barely fulfilling this condition, that the size of the experiment should be smaller than the dead body wavelength of the action, then you start losing some of the signal. But this factor is dependent on the orientation of your experiment. If you turn it like that, you will see a change in the signal. So this is a very rough directional effect that can be obtained automatically in a haloscope if it is big enough. There are more ideas in the market, and this antenna provides a very elegant way to measure the velocity distribution. It turns out that this effect that I just mentioned, there is a second order effect, that is that these photons that are emitted by the dish perpendicular, they are not exactly perpendicular. There is a small parallel component that is dependent on the momentum of the action. So if your receiver here is not just a single detector, but it's a pixelized detector, you could actually measure, in the case of a positive signal, you would measure directly the velocity distribution of the action, which is very nice. Okay, I mean, we are not yet there. We need first to have a positive signal. But in the case of a positive signal at some point in the future, these experiments would be extremely motivated, and there would be a lot of funding to make as big as antennas as needed to have a signal there.
So in this case, we're talking about astronomically produced axioms, right? Not axioms produced in the lab.
No, these are dark matter.
Dark matter axioms. Okay, so it's kind of the same with the whip wind, where it's the idea that the Earth is moving through stationary dark matter. Okay, gotcha. Thanks.
Only that if we have actions instead of winds, it will be much easier to detect this velocity distribution. So apart from these efforts to go to higher masses, there are also proposals to go to even lower masses than ADMX. This is comparatively maybe not so much motivated, but still it's interesting. You remember that there were models, isentropic windows that allow to have as low mass as almost arbitrarily low mass and have the right amount. So it's interesting to explore some of these possibilities. Going to even lower masses with a conventional haloscope concept is pretty easy, because you go to even larger volumes, so there is no technological challenge. The challenge here is to find a magnet big enough to host your cavity. So there are a few proposals that are just proposing to use existing very large magnets and just put a cavity with relatively mild parameters, experimental parameters, and then you get you should get a good result. And for example, there is the Clash proposal in Frascati that they originally proposed to use a magnet called Chloe that was there. At the end, this magnet is not available for this type of experiment, but the proponents have moved to another magnet that is also very large, similar to this one, called the Finuda magnet. And okay, it may happen in the future, such an experiment. There is also similar proposals in South Korea in this CAP institute using toroidal magnets. It's also being contemplated. And there are also ideas to use a similar thing in the large Jackson magnet that is for helioscope. So it will be to turn this helioscope experiment into a helioscope. I will talk later. And also there is another idea that depart completely from the conventional helioscope. So if you go to the lower masses, then of course to aim for a resonance in a cavity is unpractical because too big cavities. But then one can one can have a resonance in a different way. One could aim to just put a coil, a pickup coil in a strong magnetic field in such a way that you can pick up the signals from the induced by the action that magnetic field, and to also gain some resonance, to get some resonance, not by physically resonating the mode in a cavity, but with a circuit. So there are several implementations of this generic concept of using a pickup coil and resonance circuit, and there are already first results with relatively small tabletop experiments. There is a group in US, Palabra, that have already delivered several results with a very small prototype of 2 centimeters size. But there are plans to do this on a much larger scale, and the best prospects promise sensitivity down to the QCD band, but at lower masses. This is 80 megs, so we are talking about much lower masses than 80 megs. Of course, you need extremely challenging parameters like magnets at the cubic meter scale with many Teslas. So this is also a challenging project. There are also other teams called Team Radio at Stanford, and there is another one. Okay, they are not exactly similar, but they all could be categorized in this family of pickup coils plus resonators or shaft that also deliver some data with a small setup. More recently, there is a collaboration that is not working on action, is working in antimatter experiments on base, that they have done something similar in their setup. They have turned it and produced a byproduct result on actions using this idea of boxing. There are more things that I don't want to spend much time, but there is also experiments also based on NMR techniques looking for spin precision signals. So these are effects expected produced by the dark matter field, assuming all the couplings, not the asymptotic couplings. So either the very blue field, the very action to bloom term could produce, due to the oscillation nature of the dark matter field, could produce signals in NMR experiments. Also, coupling to Fermions would produce this type of signals, and there is an experiment called Casper with many implementations that are also trying to look for this type of signals, and these signals are projected in parameter space different from what we have been showing these days. Action electron or action fermion coupling. Also, the Quarks collaboration in Italy have one setup, or at least one setup, looking for spin precision. There's also another idea that I'm not sure if it's having too much consequences in the laboratory, that which is the possibility to see dark matter induced atomic transitions. And okay, the idea is to adjust with lasers to adjust the gap between atomic transitions to the action energy. So you should expect the transitions produced by the dark matter. And this is not sensitive to the action photocooling, rather to the action electron coupling or to the action nucleon coupling. Okay, there is a seminal paper on this by CTV, and as far as I know, there is an experimental team called Axioma that was trying to follow this similar, to make some laboratory implementation. So just to wrap up a little bit, dark matter experiments, I have put once more the range of masses that were suggested by these cosmological models that we'll talk about on Tuesday, superimposed to the same plot as usual our yellow band here, and all the experiments that have produced results. In green are all these haloscopes and experiments looking for dark matter actions that have produced exclusion limits, exclusion regions, with ADMX there leading the race at very low masses. But new players here. For the moment, they have explored very thin mass regions. And much more to the right, we have helioscopes that I will talk about now. And in thinly colored areas are some projections that have been proposed by different things. Okay, so you can see that there is a quite big fraction of the yellow band that is we have the promise to explore in the future. But as I say here, this is a bit some caution because some of these predictions are really optimistic. So there's a lot of R&D still to be done to get them realized. Some others are more realistic, like certainly ADMX. We believe is capable to explore all these boxes here that is indicated by the projections in the next year. Other predictions are probably less clear.
So I know all the experiments on this plot are assuming an axion-photon coupling, but are all of them also using the axion to photon oscillation, or are any of these experiments looking at the coupling in some other way?
All these experiments are looking in some sense to this axion photon process. In a cavity, well, the axion photon oscillation one-dimensional is not probably a right analogy, but doesn't really matter. It's the same. It's the same process. You have a static magnetic field, and the action wave transforms into a photon. The photon is a resonant state of the cavity, but basically it's the same. It's the same. All of these experiments. Are looking at the same phenomenology of the action.
So these atomic transitions, I mean, I guess these would be pretty sensitive to the mass. And it's possible this was a previous experiment that you mentioned, but I mean, could you also look at some kind of deviation away from hyperfine splitting or something like this?
I think a deviation of the line due to the action.
Correct. Yeah.
I don't know. Usually, as I understand, you're looking for these states getting populated by the action, but I don't know if the action would affect also the line itself. I don't know. I haven't heard about maybe.
But at least there's not an experiment that you know is already doing something. Well, that's already doing this.
In the context of the action.
Correct. Yeah.
There's one more question online. I'll ask it.
So online, there's a question by Igor, and asking about the timeline of the realization of the dash domains on the plot. Is it more like 1 year or more like 10 years?
That's a very good question. Some of them are of the order of the year of few years. Like for example, well, I mean, for example, ADMX is currently running, so this is evolving year by year. So this will happen in the, let's say, a few years. I haven't yet talked about helioscopes. This is my next topic, but Baby Jackson is getting built, so this bound from gas will improve. The one of Baby Jackson certainly in the few years. The rest of lines are more aggressive, and some of them, even if some collaborations have put some gear in there, it's not big leap because there is a lot of R&D still to be done for those, all these little experiments here, really to have the sensitivity to claim that all this can be explored. And of course, MATMAX is extremely challenging experiment. So I would say this is minimum a decade apart, if not more. So it's a combination. So every line, that's why there is a lot of information here that one has to take with caution. There is a lot of room for new ideas still. There is one should not think that this is given. Also for young people to jump in and to contribute. More questions? If not, I move to the third category of experiments, and this is, let's say, the last part of the course. And okay, again, we have the same concept, but now the source of action is going to be the sun. Source. But the detection is happening in the laboratory at the Earth. And again, we changed regime, and then we're going to change technology. So that's one of the main messages of these classes, that we're in a field in which we touch many different technological know-hows that are not typically in particle physics groups. Now we are going to deal with X-rays instead of microwaves. So as I already mentioned, the first day, the sun emits actions in a way that is at least one of the channels, the one that we call prima of solar action, that are produced by the same process. So action, photons from the solar plasma are converted into actions in the electromagnetic fields of the solar nuclei. This prediction is very robust. As long as we have an action to photon coupling, we expect this type of. This can be computed. This basically the shape of this signal is basically solar physics. There is no uncertainty. There's a very recent paper quantifying the systematics behind the solar physics. It's at the level of 1% in most of these energy names. And the only unknown ingredient is whether there is an action or whether this is this action to photon coupling, which is multiplying this cube, normalizing this cube. Yes.
So I know that I don't know too much about solar physics, but I know that there are some mysteries that exist, some things that solar physicists don't quite understand. Do any of those mysteries pose challenges for these experiments?
No, the only I don't know what do you understand, but there are two categories of models based on different data, use cosmology and these two categories of models. Okay, they have some tension, so probably this is one of the mysteries. But this is because we know so well the sun that we start having we call tension as something that differs 5%. So it's something completely different from astrophysics in other objects. For example, in this paper that I just mentioned, they do compute the action emission using these two category of models, and they do find a difference of the order of 4 or 5%. So if one wants to be very cautious, I would assign a systematic error of 5%, which is really small for our purposes for our discovery. So yeah, indeed there are mysteries, there are systematic. There are room for systematic and non-systematics, but we are talking about effects that are small for discovery.
5% seems significant, no?
Well, for a particle physicist, yes, but for astrophysicists in general,
Got it.
no, there are things that are much more uncertain. Well, this means that this does not jeopardize discovery signal. So once you have a positive signal and you want to extract the action photon coupling from this, okay, you will have a systematic error of 5% in your estimation. But we are happy with discovering the action with a 5% error. So this is a parameterization of this Q. So you see the energies here. We're talking about few keV. So these are actions there are very different actions than the Dharma actions. We're talking about relativistic actions of keV energies. And this, okay. And this is basically the basic signal one looks for in action helioscope, action experiment looking for solar actions. But if the action couples to electrons, which is something, as you know very well, is model dependent, it's not given, not necessarily, but it's an option for some models, then you have additional channels of production. So this is the Primakov, the basic channel based on the action photon coupling, but then we have a Compton that already appeared in the past for in astrophysics, no? Quantum, Restralon, and some other processes that are based on the action electron coupling. That may happen also in the sun. And in model dependently, in some cases, if the model has this coupling, this population of actions may be even more important than the model. So it's nice to have it in the one, but not to rely 100% on it. So there is a very nice recent computation of what do we expect from this action electron coupling, and you can see that this red cube represents the so-called ABC solar action flux. ABC comes from the initials of these processes, action recombination, Compton, and Restralon. And these actions are still X-rays, but they peak towards lower energies, and it has these very characteristic peaks because some of these processes are produced monochromatic light. They are basically transitions from nuclei that instead of a photon they emit an action. So this is very nice because if one day we have a positive signal, you could cross-check with detectors of good energy resolution if these peaks are there or not, and what is the shape exactly, the spectral shape of the signal. There are more possibilities for action emission in the sun. Action nucleon coupling should also produce some monochromatic lines from nuclear transitions, but in general, these emissions are very weak if one takes into account the current bounds of this coupling. So the values of this coupling corresponds to fluxes which are very small and usually not detectable. More interesting is something that has been studied very recently, so it's surprising that it was overlooked in the past. But the action of photon coupling, it also allows for another mechanism of production in the sun, that is photons or plasma, photons in the plasma, interacting with the macroscopic solar fields, not with the fields of the nuclei, like in the case of the Primakov actions, but with the macroscopic solar fields. Of course, we don't know very well what is the macroscopic magnetic field of the sun, but it's reasonably bounded, so you could produce upper and lower bonds. And for example, longitudinal plasmons converting into these fields would produce some spectrum, some distribution of actions in the range of 0.1 kiloelectron. So it's much lower than the Primakov spectrum, but it's still of similar intensity. So it offers an opportunity of directions. And this was very recently proposed and studied. And also there is another channel from transversal plasmons, but this one is depending on the mass of the action. It produces different possibilities depending on what is the mass of the action. Anyway, this is just for completeness. This has not been served to this is too recent. So how to detect these actions? Again, we have the action helioscope that is something very similar to what had been explained already for the other categories, but adapted to the sun and to the X-ray domain. So, and this was the first concept was proposed also by CPD in the same paper where we have the helioscope concept. So it's really a seminal paper for us. This one from CPD in '83. It was later on refined by some other people, Van Bieber and Raphael, by adding the buffer gas technique that I will describe in a moment. So we have the same concept. We have the actions coming from the sun with energies at the keV range. they mix with the photon in the magnetic field. And at the end of the magnet, we have some fraction of them converted into X-rays with the same energies as the original action. So what we need to put here are X-ray detectors with very low background, and we try to see an excess of X-rays over the background of the detector. As usual, this background can be determined experimentally by switching off the magnet or not pointing to the sun. And okay, you can use the same philosophy as with the light shining through wall and calculate this probability. And again, we have the typical dependence with the magnet strength squared with the length. And we have again the same effect as with the LSW. So if the condition that the oscillation length of the axons is larger than the magnet length, then we can assume that this is all what we have. But if not, we will have a drop in sensitivity, and here's this effect in the exclusion plot that we have for
What is the expected energy range? Thanks.
What's the expected energy range for axions coming from the sun? I know you said they're keV-ish, but is there a
Yeah,
spectrum there?
1 to 10 is this one. This is the spectrum. So this is
Oh, right. Okay.
probably from 1 to 10.
Got it. Okay.
keV.
Thanks.
And the ones coming from action electron, they are a bit more, less than 1, a fraction of keV, a few keV.
Okay, thank you.
So this is the energy range we need to minimize the background of our detector. This is one technological challenge that we have to address. So as I said, if the mass of the reaction is such that this condition is not anymore fulfilled, like in the case of light shining through wall, we will start losing sensitivity, and this happens because of being energies at the keV. It happens to higher masses. That's why helioscope exclusion plots are flat to until higher masses than the case of laser-based experiments. But still, this ends up happening at some point. For the case of typical sizes of these experiments, this happens at the 0.1 electron volts, something like that. 0.01, 0.02 electron volts. And then there is a technique to push these to higher masses. And this is the so-called buffer gas. But sorry, before that, I have as usual the figure of merit. So for you to understand the main experimental parameters. So the ones that enter the probability of conversion, B squared, L squared, and the area of the board. This is new because the flux of solar actions is not a laser beam, it's not a beam, you have a big flux. So the bigger your magnet, the bigger the amount of actions they will contribute to the scene. And then you have detection parameters, efficiencies of detection, efficiencies of the optics. I will say later on what is optics, and background of the detector, and of course exposure time. So what is this buffer gas that I mentioned before? So this is a trick to gain coherence for axial masses that otherwise would not fulfill this condition of the oscillation length to be big enough to fit into the magnet. So by putting a gas inside the bores of the magnet where the magnetic field is, you impart an effective mass to the photon, and then it changes the definition of the Q. So it's like you can match the wavelength of the photon and that of the action better, and recover the coherence condition. So it's like now Q is not anymore m squared over 2e, but is m squared minus m photon squared. So this changes a bit the previous formula, and you get something like that. So for example, in vacuum, the probability of conversion, or equally the number of photons that I get from the conversion, is at a given value that is independent of the mass of the action up to some point. At this point, you start losing sensitivity because we have this loss of coherence. If you put a gas inside the magnetic field, you gain the coherence, but only for a small range of masses around the mass of the effective mass of the photon, the reflective mass of the photon in this gas. So and this value you can choose because it's basically depending on the density of electrons of the gas. So you can change the pressure of the gas and you move this peak.
So could you use this to scan over mass range?
So in this mode of operation, helioscopes become scanning experiments like the helioscope. Only that this thickness is not that small as in the case of helioscope. We are not talking about 10 to the 5 step, but more about 100 steps.
And does that vacuum line extend left forever?
Yes, this is.
So then, sorry, follow up to that. The vacuum, I mean, it seems like you could see a lot more using the vacuum than you could with these small little peaks.
This is because it's a log scale. If you put the linear scale, it's always the same. So the vacuum is the first step of the pressure
Okay.
one.
Okay, got it. Okay, thank you.
So this is usually known as phase 2 in helioscope experiments. So and usually when you bound a helioscope, you run it in vacuum primarily because you want to have a very good bound on the action photon coupling at low masses. And then you turn to phase 2, and in phase 2 it's a scanning experiment. So you take a little data in one point, then you move to the next one, and so on. So before giving information on the status of helioscopes, let's mention that there are other ideas that have been proposed in the past on which could be also considered helioscopes in some sense, very sensitive to solar actions. And one of them is the use of underground experiments primarily built for winds. They could also be sensitive for actions. To solar actions. One of the techniques that has been used in the past is the use of the Primakov-Bragg effect. This is basically the conversion of these actions into photons using the electromagnetic fields of the detector. So you don't have magnet. You use the same detector looking for winds, but it transforms these actions into photons. But in addition, you use if your detector has a crystalline structure, you should expect some Bragg effect in addition to this Primakov, so that this conversion is highly dependent on the orientation of the crystal planes with respect to the line of incoming direction of the photons, of the actions, right? And then this time, because of the movement of the sun or the earth, you expect a very characteristic temporal pattern. This can be computed carefully with the position of the sun and knowing the crystallographic information of the detector. And this has been used as a byproduct by many experiments in the past, looking for winds like Edelweiss or CDMS, gamma itself. In general, the sensitivity of the action photon coupling, even if it's better than not using this trick, is still not competitive with standard helioscopes. And okay, you probably have heard about this excess in xenon 1 very recent. So in principle, xenon is once more is a wind experiment. It's not designed for actions, but it's such a big volume that if you do the numbers, you could in principle even without this crystal structure, so ignoring this effect of the Bragg, you could invoke this conversion, and there are different mechanisms this can happen. You can look for actions coming from the Primakov effect in the sun, so action photon coupling, or the ABC action, so action electron coupling, and also at the detection side, in the experiment, you could invoke action electron interaction, so again action electron coupling, or also Primakov effect, so action photon interaction in the electromagnetic fields of the nuclei of the signal. Yeah. So there are several combinations. So okay, this recently was very much discussed because the Xenon collaboration has reported a small excess at low energy. These are the experimental points. This is their background model, and there is some excess in the first two, three beams, which okay, among different possibilities, the option of having solar actions producing this excess has been tested, and in principle, if you ignore constraints from astrophysics, there is a nice solution, statistical solution. It's favored with 3.5 sigmas over the background solution, or the background hypothesis. But at the end, when you plot the interpretation of this excess in terms of action photon coupling and action electron coupling simultaneously, so taking into account all possibilities, so that they are detecting these two different channels from the sun, and they could be detected via the two different channels at the detection site. But you have that in principle all the points in the parameter space that solve the excess are excluded by astrophysics, either by the stellar cooling mechanism in the case of action electron coupling, or by solar physics for helioscopes that are not here, but the gas limit is somewhere below here. So either by one or the other is excluded. So it's difficult the interpretation in terms of solar actions.
Sorry, before you go on to the next slide here. So if we're not saying this is solar axions, and we want to explain this is xenon excess with axions, how do you avoid these stellar constraints? Or can you?
Solar actions you cannot, because it's not that my intention. It's quite big. So I think you can say, okay, astrophysics is not, there is some systematic error, so they can move. You can imagine that some of these moves may move in the future, but not as much as 1 order of magnitude. So the xenon excess interpreted only as action electron coupling. So you put the action photon coupling to very low values, is somewhere here, and the limit is here. So we're talking about 1 order of magnitude. This is the limit from the R parameter that I mentioned in the previous talk, or the white dwarf is here. So this is the hint on the white dwarf. So this is a hint. So the two things are really not overlapping at all. So it is difficult to understand. And I do the opposite. So I ignore the action electron coupling, only action photon coupling. So we have either this or this, whether I invoke inverse Primakov effect or not. But the gas limit is somewhere below 10 to minus 10. So this is really big tension with gas. So and the combination does not help either. So I think solar actions is difficult to, very difficult. There is the possibility to be cosmological actions, cosmological Augs. They will not be action Augs. This is still a possibility, but not so motivated. This can be Augs as the matter.
Excellent, thank you.
So I don't quite understand what the hypothesis is if the xenon 110 excess were axions or outs. What's going on in the detector itself to cause the signal?
It could be several things. It could be that actions excite directly the electron because you have action electron coupling. So this action electric effect. So it's like a photoelectric, but with action. So it's the same the same type of process involved in the ABC axis in the sun, but in the other way around. So the axions interact with electrons, or you have a sort of a inverse prima-core effect. So axions interact with electromagnetic field of the atoms of the scene, and they turn into photons, and these photons are detected immediately detected in the scene by photographic or whatever. So at the end you have the same spectrum, okay, with some detector response like that. All this is put into the model, and you let free this coupling constant. The red cube is the best fit to this.
Okay, so basically the axion electron coupling and the axion photon coupling are mimicking the effects of a nuclear recoil in the detector.
Both are capable of mimicking and produce reasonable fits. Okay, there is a preference you can it's not indicated here, but okay, this region will have a best fit. Well, for example, but all the region is equally good statistically. So you could in principle fit the success with both electron coupling and photon coupling.
Okay, thank you.
It's electron recoil.
So it's electron.
Because we said this plot I think was looking at electron recoil specifically.
Yeah.
Okay.
This is not the
It's not
standard
a standard analysis.
analysis with nuclear recoils. This is electron recoil.
Okay, I realize that. Thank you.
There are ideas which are a bit more less orthodox. Well, in fact, this is based on a very old an idea which is old at the time of the proposal, but has been revived recently in this paper, which is to use a big TPC, gas TPC, as a helioscope, and it brings two advantages. One is that there is not anymore a privileged direction, so you embed this TPC in a big magnet, and wherever the sun is, you try to detect this action. So this has a penalty. You don't have this L square dependence, but at high masses it could be compensated, because the very gas of the TPC that you need to, okay, this would be a gas TPC, not a TPC. The very gas of the TPC would be used as a buffer gas. So this is a nice idea, but it's something on the paper for the moment. So let me go back to the standard helioscope idea and tell you a bit what has been done in the past. So the first implementation of this idea was done in Brookhaven in the 90s. Then there was a helioscope called Sumiko in Tokyo. But the state of the art now is represented by the CAST experiment that has been running at CERN for almost 2 decades now. It's almost finishing the experiment. So basically, the idea of this helioscope is what I just mentioned. Have a magnet, strong magnet, which is of the same type of the light shining through wall, because the length is important. But the innovation of CAS with respect to previous implementation of this idea is the use of X-ray optics. I would say a few more words about it, because this is one example of a technology that is not typically used in particle physics, but there has been a lot of development of this equipment for X-ray astronomy. So it's a connection with this discipline. Basically, this acts as a lens, but for X-rays. So these figures that come more or less parallel from the sun, they are concentrated at a very small point here. So we can increase the signal to noise ratio by a big factor. And then we have all our photons concentrated in a very small spot. So we can concentrate here a very good detector with very low background, surrounded by shielding, because the background of these detectors at the X-ray regime, then it comes from basically from cosmic rays and radioactivity. So this is the same type of problem than we've experienced on the ground in underground laboratories. This is a picture of CAST. This is basically once more one of the early prototypes for the LHC that was recycled to do action physics, like Oscar did also. So this is it's a superconducting magnet with two boards, and it was placed on a platform that allows to move this magnet pointing to the sun. So it's sort of like a fancy telescope. It follows the sun for only 3 hours per day, because we cannot take it more than plus minus 8 degrees. And at the end of the two ends of the magnet, during the lifetime of that, many detectors have been installed and developed and to data to produce limits. I have a little video from the experiment, so you can see in quick motion how is the life of cast in one data taking run. So I don't know why it does like that. You can see that action experiments with casts are not anymore tabletop experiments, so they become to be some big things. Okay, so you see that basically during the 3 hours, during the 1 hour and a half that in the morning and another 1.5 hours in the evening, that the movement of the magnet is capable to track the sun. Then you have this movement, and when it finishes, it goes to the parking position and starts over again in the yeah.
Do you know why they couldn't move it more? Like put it on a higher platform or something?
It was not a problem of the platform, but the mechanics of the magnet. So this magnet was built to sit down in the LHC, not moving. So it was not foreseen to be moving so much, and the engineers that make it say don't think it more than 8 degrees, because we don't know what happened. Maybe some legs break. So it's a purely practical limitation. So of course, in the next experiment that we are starting now, Jackson, that all this will be built from scratch. So this will happen. So we will move the magnet much more.
Got it. It's cool that they repurposed that though.
We could.
It's cool that they repurposed that in that way.
Yeah.
Yeah.
And from many of these early results have been done recycling equipment. So experiments also with the optics, we did the same thing. So this is the this is a bit of historical information. I will not go over it. CAS has been running since the 2003 or so, producing different results. The one that is typically quoted now, which is the last limit from CAS, it was obtained with the so-called Jackson pathfinder. So Jackson is the name of the successor experiment of CAS, and it was already it was called like that because it was testing technologies for Jackson. So you probably don't see this picture very well, but this is the end of the detection, one of the detections like the most advanced of CAS that help us produce the last result. And what you see here is this is the magnet, one of the boards of the magnet, and here in this case you have the optics that makes these photons converge into a focal spot that is placed here, and then we have the detector just placed at the focal spot. This is one of the so-called micromegas detectors with gas inside. It's a gas detector, very low background. And the combination of this type of technology for detection with an X-ray optics, it was a first in this kind of setup, and that's what allowed improve previous results and produce this limit that is, as you can see here, is practically the same as the one you get from personal bright stuff. So it's the first time I'm explaining produce a limit on the actual photocoupling that is competitive with astrophysics. This is a few years old. This is from 2017. Okay, some more data. How this data looks like. So this is the background spectrum obtained by this type of detectors. This probably doesn't tell you much, but this is extremely low background. This is obtained by using very clean materials, like the one used in wood or WTD experiments. So it's all know-how from low background techniques, low radioactivity materials, shielding neon beaters to tag the presence of cosmic radiation and inject it offline. And at the end of the day, you have something like that. So this is our detector, which is placed in the focal spot, and it's pixelated, so you can see what's happening in the detector. You put the source, X-ray source, far at the other end of the magnet, so you calibrate both the optics and the detector. So this beam of photons are concentrated by the optics, and they arrive to the detector, and you get this type of maps. This is something very small, 5 millimeters. This is the focal spot calibrated by the source. But these lines are computed by X-ray tracing models, and the actual colors are the actual data. So there is a good agreement between data and the model. So this is a combination of the work from the X-ray optics team, who does things like that in X-ray astronomy research, and the detector team. And of course, then you have to take into account that the source does not represent completely what the actual photons from the sun do, because the source is not so that infinite, it's only 50 meters away. So one has to use this data to validate your model, how the optics focus these photons slightly off focus, and then recompute it how this would be for the actual signal. This is the line that one expects for the signal in case we have photons coming from the sun, actions coming from the sun that then converted into photons. And this is actual action data. So this is the data taken in all the runs with the magnet pointing to the sun, and you can see I think there is 6 months of data. We have only a few counts, so extremely low background. Only 3 counts really inside the high likelihood region. And this is basically the data that was used to produce the So this is the best result so far in the frontier of helioscopes, and now the field is facing the next generation experiment, which is embodied by the JAXO experiment, which is the largest collaboration in experimental physics, more than 100 people, which is still far from the big Atlas type of collaboration in particle physics, but certainly big for actions. So JAXO is the same concept as Jack plane forecast, but pushing the parameters of the experiment to the maximum that is realistic. So building a completely magnet that is not recycled, but is built with the figure of merit of the action helioscopes in mind, to keep it with X-ray optics, tailored to the action energies, and also to push detector technology as much as possible. Okay, you can see basically the parameters in the figure of merit that are most important to push the figure of merit of action. So there's been quite some work in the last years, and there is already since some years ago a conceptual design for this experiment fixed, and this is something that is a little bit how this should look like. You can see that we are talking about a large-scale experiment, not anymore a rooftop experiment. And basically the concept is the same as CAST, but you have a much larger magnet. It's not anymore an accelerator magnet for a particle physics. It's rather more like a detector magnet. It's a toroidal configuration. And in the space between the coils, there are several boards in which the equipment is attached to. So you have several opportunities to detect actions. So there are 8 different detection lines, each one of them with an optics of 60 centimeter diameter, each of them, that focus the photons from actions into a small spot 5 meters away in the focal spot. And each one of these spots are imaged by very sensitive low background detectors, which are surrounded by shieldings that are here represented by a box, but it will be much more complex. And all these can rotate and can track the sun for a much larger time than cast. This will be taking into account at the same time. So just to illustrate the connection with different technologies, like we have been doing in the previous classes.
This is a very naive question, but can these types of detectors track the sun through the earth? Okay,
You can point down the actions to care about the earth, they
Right.
traverse it equally.
Okay.
So yeah. In fact, cast already did this because we moving the magnet minus 8 degrees up to plus 8 degrees.
so is this, is YAXO tracking the sun 24 hours a day?
It's tracking roughly 12 hours per day. Depends on the day of the year, the day of the year. But on average of 50% of the time. Roughly.
Is that a physics thing or just a manpower thing?
This is a practical decision because at the end you need also time to take data without tracking the sun to measure the value of the detector. So we believe that pushing to more than 50% of the time, it will not make us gain time at the end because you have to stop this there and take data. So the specifications of the platform was set to plus minus 20 something degrees, which is enough to track the sun for 50% of the time in a location like Hamburg. This will end up built at this Hamburg, which is also an advantage because the sun doesn't go so high. So superconducting magnets, again, this is common to all action experiments. This is a very important technology, and this is why this project is has been always connected to CERN, which is the place where the know-how to build such large and powerful magnets is mostly. So I will not go into so much technical details. Let me just flash over optics. This is a very nice equipment, and how these optics work, I don't know. This is something that, as I said before, it's not typically known in our community, but this is something developed for many years in X-ray astronomy. So X-rays, obviously, they don't interact with lenses like optical photons, so you need something else. And the physical principle that is used is the fact that when an X-ray hits a surface, a mirror, with very small grazing angle, then you have a very high reflectivity value. This only happens with very small grazing angle. Therefore, what one does is to build this configuration of mirrors that are a set of nested mirrors. This is a cartoon. In reality, you have many of those. Depending on the application, it could be hundreds of these nested mirrors which are slightly tilted. They are not cylindrical, they are slightly conical, one inside the other. So that, and they are very thin, so that these rays come with a grazing incidence angle with the surfaces, and they reflect. Usually you need two such reflections to simulate the effect of a lens with good approximation. So these are exquisite equipment built with a very high precision, and at the same time very robust because they are usually sent into space for these X-ray telescopes. At the end, the result is that these X-rays they are focused much like a lens, and they go to the focal surface of the focal spot. And CASM has been the first telescope in using this concept, and we borrowed one of these lenses from Abrixa's X-ray mission, and it was placed. So it was again an example of recycled. It was placed on one of the boards of class, and it's one of the early results from that. Later on in the project, for this Pathfinder system that I mentioned before, a specific X-ray optics was built for the experiment. And that was the first time the X-ray optics was built specifically for an action experiment. Also as a Pathfinder for JAXO, because the optics of JAXO will need to be built. So JAXO will have many of these optics, rather big, 60 centimeters. For the case of actions, we don't require an exquisite imaging capability like in the case of astronomy. We just need to focus this photon somehow. So this helps decide over the technologies that are present in the market, let's say, in this astronomy. And basically what was done was basically to piggyback on developments done for the Newstar telescope, which is something that some mission that is now taking data in space. So these optics exist in space. So and the way to build them is relatively flexible. So it can allow us to do what we want. So to design an optics that is specifically optimized for the action spectrum from the sun. And that's what is being done. And then we need the technology to detect these actions, these photons from actions, and the baseline technology for this is this gaseous detectors based with micromegas readouts. So basically, what we have is a small chamber. We only need to image a very small spot of less than a centimeter wide. So this is the end of the tube in vacuum that comes from the magnet. So the end of this big tube that you see here. This is just a few centimeters wide. So the photons come inside. They interact in the gas. They produce ionization. And this ionization is projected to the readout plane and read with pixelized readouts. So you have very precious information on whether this ionization is compatible with an infrared or not. So you can do offline projection and so on. All this is built with a special clean material. So all this is know-how from underground experiments, but this is not happening underground, but it is symptomatic. And as you can see here, copper is a typical material that's very clean, and everything is embedded in a LED shielding to block external radiation that produces magnet. And this is another picture of these detectors in the left castle. And a picture of the window. So this is a challenging part. We need a window to stop the gas, to separate the gas from the vacuum, but at the same time, the X-rays need to go through. So they have to be very thin windows. So you don't lose efficiency, but it has to be strong enough to stop to block the gas there, not produce a leak into the system. And okay, this is a level of background that have been achieved with this technology, which are record levels for this type of purpose. And this is the goal for Yaxo. Yaxo will improve at least one order of magnitude the best background level for Casper. This is something that is being developed at the moment. One could also imagine to detect these X-rays with different technologies, and there are several other technologies being proposed in the community. It is just for your information to have this names in mind. I think the detectors, which is a more modern version of the micromegas gaseous detectors, so the same principle, but with a chip instead of a PCB here. MMC detectors, these are superconducting cryogenic detectors, similar to volumetric type of detectors. These are very nice because they have extremely good energy resolution. So in the case we have this action electron population, positive signal, this type of detectors would be very motivated to look for this. Yes.
On your previous slide with the EXO collaboration trying to get very low backgrounds, why would they choose lead shielding? Isn't that very not radio pure? Aren't you going to have a lot of radioactivity from the lead shielding itself?
No, if the lead is clean enough, is pure enough, it's not radioactive.
Okay.
There is no. The only problem is the lead-210, which is an isotope that is produced that is with the lead, and it's radioactive. And sometimes this underground experiments use archaeological, because archaeologically this lead-210 has decayed, has a 20 years old of decay.
Okay.
But okay, this is onion layer strategy. So you could choose a very clean material close to the detector. And typically the closest material is not lead but copper. The body of the chamber is made of copper, very clean copper. And then you can start putting lead, very clean lead, and usually whatever remaining radioactivity the lead has is blocked by the copper. So and the next layers you can relax
Right.
the specifications of this lead. It can be more normal lead.
Okay.
Because it's blocked by the inner side of the sheet, which is clean. So yeah, but lead is a typical material to shield. Of course, has to be pure lead.
Okay, thanks.
The problem with lead is that when used on surface, when you have these cosmic rays, you cannot avoid the presence of cosmic rays, and lead is a target for these cosmic rays, and they have secondary effect. So this is something that has to be taken into account. So Baby JAXO is what is being built right now. So the strategy of JAXO is going to be to start with intermediate scale helioscope between GAST and JAXO. It turns out to be a successful strategy to jump to something simpler before starting building big JAXO. And this is something that is right now being built, and it will serve both as a prototype, technological prototype for the big JAXO, that at the same time produce physics, because the figure of merit of JAXO will be something of 100 times cast figure of merit. So one could see a signal that in cast is barely at the noise. It should appear in the JAXO with a signal to penetration of 100. This is roughly halfway between cast and JAXO with about and then to the 4 figure of merit improvement factor. So this is already ongoing, and we hope to have first data in maybe 2024. So the projections that I will show now for these experiments are a few years ahead, hopefully. So we come back to the plot. This you have seen already in the past. This is the current limit from cast, the best limit on action photon coupling, which is practically coincident to the horizontal branch limit. You can see it here. This is currently the best bound on the action photon coupling, and they also will improve this by such factor, and JAXO by another. We have 2 projections for JAXO, one more aggressive and one more conservative. Probably JAXO will be somewhere there. So as you can see, well, it's going to be an important step into unexplored parameter space in a wide mass range. So it will clarify all these regions that I mentioned in the second class, that it was a bit controversial what's going on there. And it will also bite a substantial fraction of this yellow band at the highness, at the milli-electron volt to electron volt aspect. So this is nice and very complementary with this happening in the helioscope region that I was describing before, as you can see. Okay, this is also to illustrate that what is shown in the other plot is sort of the basic physics case, but if we are able to detect also, we can be sensitive also to action electron coupling via the ADC action. This should be shown in some other plot, and this is such plot. So in principle, helioscopes are sensitive to the product, in that case, to the product of action electron action photon coupling, and in this case you can also have a similar yellow band and similar bounds, and then you can put here these regions that are preferred by the hints from astrophysics. You can see that JAXO will be sensitive to those. This is the similar regions projected in the action photon coupling. They are somewhere here, so they are also sensitive by JAXO. So this is one of the important motivations, because this population of solar actions coming from the action electron coupling, when one takes into account the bound on the action electron coupling, is very strong. So there are at present no experiment sensitive to values of the action electron coupling that are not excluded by astrophysics. Right? This will be the first time with the big JAXO. Will be for the first time. By the way, I forgot to mention that this wiggly part of the cast bound is this phase 2. that I was mentioning with Igor. So this is again the same thing like with Irastorza, that every day we will change the pressure of the gas and take data again. So this is the envelope of all this. Data. And then if one day we have a positive signal in a telescope, in Jackson particular, then you can do many things. You can measure the axion mass. This we mentioned already also for Lecture4 football experience. If we are lucky and the signal is close to the place where the sensitivity goes up, then you have sensitivity to the axion mass because the spectrum gets distortions from this onset of oscillations in the mass. If the mass is somewhere here, if the action is somewhere here, we could determine the mass. And if we are lucky and we see both action, photon and action electron induced actions signal, then the overlap of both populations can be used to extract independent information and determine independently both couplings from a positive signal injection. And this is studied in this paper, and this is the region of parameter space in which this could be done. If we are. And I think with this, I finished my course just on time. So, no, this is the same slide I did at the very beginning to stress again my main message that okay, I think actions are very well motivated and this is very strongly motivated by theory, by cosmology, by maybe also by physics, you know. And as you have seen these days, a big fraction of the parameter space is at reach of experiments being proposed and being carried out. So it's an exciting field, and okay, this is an overall picture. Okay, overlapping all helioscope frontier, haloscope frontier, laboratory frontier. Okay, there is a non-negligible fraction of the yellow band, hopefully at reach in the future. Still fractions to be tackled. So plenty of work to do also. So I think I finished with this, and thank you for your attention. And I hope this can be useful for you and whatever you do in the future, whether it's related with actions of or in neighboring fields. And if you have questions, you can write to me. We're happy to help you. Thank you. It's just in time. So. Not this afternoon, it's still some time.
Yes, there's still a discussion session. Okay, so thanks a lot, Igor. Stop the recording. I think, yeah, so the next session is Joachim, right? Or the general, I think it's Joachim.
Yeah.
So Stephen Happen.